Hello everyone, welcome to Griffiths Electrodynamics. This is going to be problem 4.15. Just want to say hello if you're new to my channel. If you're a returning subscriber, welcome back. And yeah, if this video ends up helping you out, or any of my other videos have helped you out, feel free to leave a comment, leave a like on the video, subscribe to my channel, things like that. Feel free to check out my membership options as well. I offer early access to my videos for membership, as well as a different membership tier gives you access to LaTeX solutions, typed up LaTeX solutions of these videos as well, if that's something you prefer as well. So anyways, let's get on with the problem. So 4.15 is here in the book, and essentially what it's saying is we have a thick spherical shell with an inner radius of A and outer radius of B. And it's made up of a dielectric material with the frozen in sort of permanent polarization given by this polarization function here. So let's just kind of think about what the problem is. We have essentially a hollow inner sphere here. So within that sphere with radius A, the inner one, it's kind of empty space. And then we have another sort of hollow, well, not really hollow, but like we have another sphere of radius B that surrounds it, and the space between the sphere of radius B and the sphere of radius A is made up of this dielectric material. It's kind of like a, I don't know, it kind of sounds like a spherical capacitor in a sense, with a dielectric sort of medium between the space between the two shells. And that dielectric material has this sort of permanent polarization built into it that points sort of radially outwards away from, the center. And it's given by this function. So the polarization gets weaker. It's inversely proportional to the distance r from the center. So it kind of gets weaker as you go to the outer surface from the inner surface. And K here is a constant. And of course it says r is the distance from the center. There's no free charge in the problem. So the only charge that's present in this problem is going to be bound charge. We don't know how this polarization arose. We can assume that there's some external field that maybe applied this permanent polarization, but now that there is a polarization, that creates a sort of bound charge inside of the material. And that bound charge is present, but there's no free charge that has been placed or anything. And so our goal is to find the electric field in all three regions by two different methods. So the two methods are going to be, one, locate all the bound charge and then use Gauss's law to calculate the field it produces. And then method two is going to be using equation 4.23 to find the displacement field D and then get the electric field from that. So 4.23 is this relation here, where the this relation here, which is kind of like Gauss's law for the displacement field. But it wants us to use that equation to find the displacement field and then use the relation that D is equal to epsilon E plus P, and we can essentially derive the electric field from this if we know D, and we do know P because P is the polarization given here. So, and then the three regions it's referring to should be obvious, but the three regions are: what is the electric field inside of the inner sphere A, what is the electric field between the two spheres, and then what is the electric field on the outside of the sphere everywhere else in space. So those are the three regions we need to find the field at. All right, so let's go ahead and kind of look at this solution here. So I went ahead and drew out the problem, kind of, and I labeled, the inner region as 1, the middle region as 2, and the outer region as 3. We have no free charge present. I rewrote the polarization function here. And so we need to find the electric field using the first method, which is essentially using Gauss's law. So I went ahead and also wrote out the derived the bound charges that are present due to this polarization. So the volume bound charge is, of course, the negative divergence of the polarization. And so just using the spherical version of the divergence, because we're using spherical coordinates here, this is a spherical coordinate function, that'll be -1 over r squared d by dr of r squared times the component, the r component, which is k over r. So, that's just going to be, that r is going to cancel. We're going to get, so that r squared is going to cancel the r on the bottom. So we have kr. So you have to take the derivative of that, which is just going to be k. And then we have this -1 over r squared. So we get minus k over r squared becomes our volume bound charge. So there is a bound charge within the volume itself inside of the dielectric, and it kind of grows. It's inversely proportional to r squared, so you get less and less charge moving from the inner sphere to the outer sphere. Then there's a bound charge. The bound charge is given by p dot n hat, but the bound charge, think about where this bound charge could exist at, right? The bound charge could exist in two places. It could exist on the surface of the inner sphere A, but it could also live on the surface of the outer sphere B. And so we're going to choose the normal vector on the outer sphere to be pointing outside, away, into free space. And then for the inner sphere, we're going to choose the normal vector to point inwards into the empty cavity of A. And then when we do our P, which is this dot n hat, so for the inner sphere, n hat is going to be minus r hat, and we're going to dot that with P, which just gives us minus k over A, because here r is equal to A at the inner sphere. And then for the outer sphere, it's going to be P dot r hat, not minus r hat, which is going to give us, is that really a minus sign? I think that might not be a minus sign here. I think this should just be KB, because that'd just be K over R. Yeah, I think that's just, I don't think there's a minus sign here. I think that might be a typo, but we'll see. But yeah, this should be K over B, right? We're just dotting R hat with R hat there, and we get K over B because R is equal to B there. So that's just useful information that we're going to need to know. So we know what the bound charges are, and the volume and the surface bound charges. Now let's find the electric field. So let's look when R is less than A. So when we're inside the cavity here, we of course know Gauss's law of E dot dA, which is equal to the total charge enclosed over epsilon naught. And because we're dealing with spherical symmetry here, we can assume that the electric field is constant for any given radius r. So, of course, our Gaussian surface, right? I'm not going to explicitly say or draw what our Gaussian surface is, but our Gaussian surface in this case is just going to be some sphere that is less than the radius of A inside of this cavity here. So the total charge enclosed, of course, would be any free charge plus any bound charge, but there is no free charge. That the problem states that, and when we're inside of here, there is no bound charge. All the bound charge is going to live on the boundary of A and on the boundary of B, so there is no bound charge. So when R is less than A, the bound charge is 0, so that means the electric field must be 0 for this relation, for Gauss's law here to hold. So that part's pretty easy. It kind of just falls out of Gauss's law like that. But let's do the third region. So when R is greater than B, we need to figure out the charge enclosed. Well, here we are going to have bound charge. Of course, we still don't have free charge. That's just the problem doesn't give us any free charge. But we're going to have, our Gaussian surface is going to be some sphere that encompasses this entire sphere. So the bound charge we're going to have is going to be all of the surface bound charge and all of the volume bound charge. However, we know that the surface and any bound charge that gets sort of induced because of a polarization? Well, typically what happens is you have a neutral dielectric material that gets polarized, and now you get this sort of net charge distribution, but the total charge to begin with, the total net charge was 0 because the object wasn't polarized before, right? And problem 4.14, we did this and we showed this, that if you sum up all of the bound charge, you get a net charge of 0. So because the only thing in this, the only charge we have in this problem is the bound charge, and our Gaussian surface encompasses the entirety of our sphere, which encompasses all of the bound charge, the sum of that bound charge should be 0. That means the total charge enclosed should be a net charge of 0, which then means that the electric field should be 0. Same as part A, same as when the radius is less than A. So when we're less than A, when we're greater than B, we have no electric field. It's kind of shielding, this sphere is sort of shielding the electric field of the dielectric inside of the sphere. But now let's look at the field inside of the dielectric. So between, when R is between A and B. So now our Gaussian surface is going to be some sphere of radius R that's sort of in between this. So it encompasses all of the bound charge that lives on A, on the surface of A, but it doesn't contain any bound charge that's on the surface of B, but it contains some of the volume bound charge that's between the two, right? So let's look at this integral. So of course we have our Gauss's law that the integral E dot dA is equal to Q enclosed over epsilon naught. Now, what is Q enclosed in this case? Well, it's going to be the surface bound charge on A times the surface area of A. So I just wrote sigma sub A is the surface bound charge on A times 4 pi A squared. That's going to be the total charge on the surface of A, plus the integral over the volume of the volume bound charge. So we need to integrate the volume bound charge over the volume of our Gaussian sphere. So that's minus k over r squared. That was what we derived for the volume bound charge, minus k over r squared. And then we're integrating that, with the volume, volume element. So it's going to be r squared sine of theta dr d theta d phi, where r is going to go from a to some value r. Theta is going to go from 0 to pi, and phi is going to go from 0 to 2 pi. So of course there's no theta or phi dependence in this integral. So that's just going to be 4 pi. When you do that integral, because the sine of theta d phi, that'll all be 4 pi. The r squareds are going to cancel here, so the integral is just going to be minus k with respect to r. So you get a minus kr, and then you just evaluate that from r to a. So what you end up getting is here, sigma sub a is going to be, well, what's our sigma sub a? If you go back up, it's going to be minus k over a. So this a squared, we have the k here and the minus sign, so minus k over a, but the a on the bottom for minus k over a will cancel one of these a squareds from the area, so you just get a single a on top. So you end up getting minus 4 pi ak from this term, minus 4 pi, that's from the integral, k, and then r minus a, that's from evaluating the bounds of the r integral. And so when you do this, you just end up getting the 4 pi ak's will cancel, but you still have a minus 4 pi kr. So our charged enclosed over Gaussian surface is a function of r, which makes sense. It depends on how big our Gaussian surface is between the two. So then the left side of Gauss's law, of course, will take the electric field to be constant around our Gaussian surface at that radius r, and of course the volume of our Gaussian, or the surface area of our Gaussian surface is just 4 pi r squared. So that's the left side is equal to the right side is minus 4 pi kr over epsilon naught. do some simple algebra, and what you find is you get the electric field is minus k over epsilon r in the r hat direction. All right, that is part A. So that is we found out the electric field using Gauss's law, but now it asks us to use 4.23, which is essentially Gauss's law for the electric displacement, which only depends on the free charge. And then we can use that displacement field to then derive the electric field from the relation between the two. So, of course, Gauss's law for the displacement field is that the flux of the displacement field through some surface is equal to the free charge enclosed. However, there is no free charge in our problem. So for our problem, the flux through the displacement field is just going to be 0 for any Gaussian surface we choose. So that means that the displacement field is going to be 0 in all three regions. It doesn't matter. There's no free charge. That means the displacement field has to be 0 in all three regions. Now, like I said, the displacement field is equal to, let me just write this here. So, of course, we know that D is equal to epsilon E plus P. So the electric field is equal to D minus P divided by epsilon naught, right? So that's where I got this relation here, D minus P divided by epsilon naught. So, of course, D is going to be 0, so our electric field is just going to be minus P over epsilon naught. Well, for the regions A, R less than A, and R greater than B, there is no polarization in those two regions. The polarization only exists in the region between A and B, right? So because there's no polarization, that means P is going to be 0 for those two regions, which tells us the electric field is going to be 0 for those two regions, which is exactly what we derived before using the previous method. However, for the region between A and B, there is a polarization, and the polarization is K over R, I believe, right? The polarization function it gave us is K over R, and that means that the electric field is minus P over epsilon naught, which is minus K over epsilon naught R, which is exactly the same field we found using the Gauss's law method in part A. So we still get minus K over epsilon R in the R hat direction. And as you can see there, that kind of gave us the answer much more quickly than using Gauss's law, which is kind of the whole point of this example, is to show that you can derive the field in these two different ways. You could just use Gauss's law for the electric field directly, and that will give you the answer. But you can also use this displacement field value to derive the electric field, and that can be much easier to get the answer for the field given that you know a polarization. Because the displacement field, especially when you have no free charge in the problem, only polarized bound charges, that's when this sort of second method becomes more useful. So anyways, thank you guys for watching. I hope that made sense to you guys, and I hope this helps you guys out and helps you understand sort of this problem a bit more. So anyways, thank you guys so much for watching the video. If you liked, leave a comment, like the video, subscribe to my channel. And as always, I will see you guys on the next video.